Right. Can people on Zoom hear me? Hang on. Okay. Now can people on Zoom hear me? All right. Excellent. All right. Uh, well, good afternoon. How's everyone doing? Ready for midterm? Yay! No yay? Boo? Okay. Well, midterms tonight. If you haven't yet received any information about that, please let us know. You should have received a seating assignment already, right? All right. And then remember, you still do have homework 3 and project 2B that's due this Friday. So after the midterm, you don't have too much of a break. Sorry about that. It's just how the schedule turned out this time. All right. So last Monday, I asked during lecture whether people would prefer to have a full lecture on tries or a half lecture on tries with a half lecture with midterm 2 review. And the vote went in favor of midterm 2 review. So we are going to have just a half lecture on tries today. That just means that you should go over the tries videos that Josh Hogg posts. They're from a few semesters back, and they'll cover largely the same content. So this is going to be kind of an abridged version of the tries lecture. We're going to miss a few key details, a few like building blocks towards the actual process of building a try, and a few like cool like subtypes of tries. But it'll still overall give the main idea of what a try is. All right. So, shall I get started? All right. So far, we've looked at a lot of these different data types, right? We've had sets, we've had maps, priority queues, lists, disjoint sets. Today, we're going to look at a new way to build a particular type of set and map. In particular, so far, we've seen these two types of sets and maps. We've seen the balanced binary search tree. Using an LLRB, we're able to get log n runtime for both contains and add. Using a hash table, we're able to get constant time. But they kind of assume a lot of things. It's theta 1 amortized, assuming you have an even spread. It's not going to be perfect for every single situation. So today we're going to be looking at a specific type of set. In particular, we're going to be looking at a set of strings. And in doing that, we're going to actually find a way to do something better than just a plain hash table. We're going to be finding a way to get guaranteed constant time runtimes. So we're going to be developing this structure called a trie. And the basic idea is that we're going to store each letter of the string as a node in the tree. We'll have extremely good performance on the get and add around constant time. But more importantly, we'll actually be able to use this to perform some special string operations that we can't really do with hash tables. So just to start off, here are two examples of how we might created a string set before. We could have used a BST, which would look something like the thing on the left. We could have used a hash table, which would have looked something like the thing on the right for some given hash function. Today, we're going to actually build it like this. So here's what our first trie structure is going to be. So we start off with a root node, and then that root node connects to an S. The S connects to an A, then to the A connects to D and M. So this is a trie that represents the words sad and sad. The idea is that if you have a path from the root to a leaf that is your word, then that is considered a valid word in the trie. So just as a quick exercise, how might you add the other remaining 4 words into this trie under this idea? So we have nodes, each represent a letter, and the words are stored along the path from the root down to a letter. Let's take about a minute or so, and then I'll come back and write out the answer. All right, let's bring everyone back. So first off, how would you add sap to this? Huh? Sorry, what? Yeah, I'm going to add a node P, and I'm going to link it to an A. All right, how do I add same? Yeah, I'll add a new node E down here and connect it to M. How about A? How do I add the word A into this? Yeah, I just start at the root, add a new node here, A. Could I do this? Would this be allowed to add A to this trie? Not really, because now I'm adding like A, D, A, M, E, A, P. There's a whole bunch of new words that I've suddenly added. So we can't do that. So it's just the A this way. How do I add alls? AWLS. Well, same thing as before. I now need to add a W here, add an L here, and then add an S here. All right. If I did this right, then the next slide should have something similar. Yeah. Now, you might have noticed that there's a bit of a problem here. Uh, we can't actually represent the fact that some of our words aren't actually a thing, right? Like, for example, this is a valid word, A. Sad is a valid word, but AW is not a word. So how do we make it clear that our set contains the word A, but not AW? And let's take another minute to discuss how you might do this. All right, let's bring everyone back. So, what do people think? Yeah. All right. All right. Yeah. It sounds like what we can do is we can mark nodes that correspond to the end of a word. So if I do something like this, here are these six correspond to the ends of all the words. And we just mark them somehow. It can be like a Boolean value, like a true false is word. Uh, in this case here, I think what I did was I just colored them. But if you want to implement it, it'll actually be like a Boolean. So yeah, you can do kind of like this. So given this structure, how do we check if this contains the word Sam? Does this contain the word Sam first? Why? Yeah, if you follow down this from the root, you get S, A, M, and M is a blue node, so we know that it's in there. Does it contain SA? No, because you go down. This node does exist, but it's a white node, so it doesn't exist in our dictionary or in our try. Does this contain the word A? Yep, because we go down, it sees a blue node that is A, that's fine. How about SAQ? No, why not? Yep, you go to S, you go to A, you don't find a Q child, so therefore you've gone off the tree entirely. You can't find it at all. So in a way, contains is going to have two ways that you can fail. So if the final node you reach is a white node, then that means the word is in your dictionary. If you don't even have a letter that's associated because you go off the tree entirely, then that also means that the word doesn't exist in our try. Now we can also set this up as a map. Here's kind of how you might, instead of having just nodes with a letter, you might also have a value assigned to them. So here's just some ways that you can manipulate a try to be used for different purposes. So using this, we're able to get a version of a try or a version of our string set that has some interesting properties. We'll go over some of them in a bit. So before we continue on, do we have any questions on how the try works? All right. So just as a quick historical aside, this is the word try is short for retrieval tree. So technically, the original inventor said that you should pronounce it tree. In practice, no one does that because tree is already a thing. So everyone just pronounces it try. So if you ever meet Edward Franklin, uh, yeah, just sometimes people are bad at writing names. So yeah, we call it a try. It is technically supposed to be pronounced tree, but don't listen to the creator. All right. So let me ask you this. What is the runtime for a try operation? How long does it take to add new things, and how long does it take to contain or to check if things are contained in it? Let's take about a minute to figure that out. All right. Let's bring everyone back. All right. What do people think? How long does it take to add a new string into this try? Huh? Constant? Constant relative to what? Yeah, constant relative to the number of different strings in the try. How about contains? Someone said log n over it down here. Yeah. O of n. Well, yeah, it is O of n. Because O is like an upper bound. Yeah, it's also constant in this case. Yeah. Both of these are constant runtime, assuming that our keys are sufficiently like short, right? That we can pretend that they're constant. It's actually independent of the number of keys. Now, you do have some weird things where you might say it's log n because there's only so many keys you can possibly put into a tree with a given fixed size of keys. Uh, but we kind of don't think about that too much in terms of the length of the key. The add runtime is theta L because you need to go down L layers for a string of like length L. And for contains, it's also theta L or O of L, sorry. You might end a bit early because you managed to drop off the tree early. So if you have, let's say, a length 10 string, then you're going to be able to finish adding it or checking if that thing is contained within a try in 10 units of time. Yeah. Why is contains O of L? Because sometimes you can get lucky and you finish early ahead of time. Like if, for example, this was our entire try, right? And we look for the word quagga, right? Q is not contained in this try immediately, so we just stop at the first letter. We don't need to keep going down the try. So we can finish early, but we can't finish after L units of work. So if we have keys that are strings, then tries will give us slightly better performance. It's not relying on even spread of strings anymore. It's guaranteed constant runtimes for both get and add, assuming, of course, fixed size strings. If you include the fact that strings might be arbitrary length, then you are going to have a longer try runtime. But at the same time, hash tables are also going to be slower because hash functions take time relative to how many characters are in the string anyway. So you'll have to do some computational experiments to figure out which one's best, depending on what system you're working with. But what tries are really good at are actually some special operations that other string based sets can't easily do. Let's take a quick look at them. So the big thing that we can do is that we can actually like get certain subsets of strings from uh, a try. With a set, you can get all the items in the set fairly easily. You just iterate through every single one of these buckets and look at each item. With a try, we can get something similar as well. But with this, you can't easily get all the words that start with A, for example. Whereas with a try, you can get all the words that start with A fairly easily. You just look at this side and we get these items. So here's some examples, right? Uh, find the longest prefix of a string that's contained within the try. So if we have the word sample, what's the longest prefix that's contained within our try? Sam. How might we actually solve this as a human? Well, we go down S, A, M. We don't see any P, so Sam is the longest one that we had. It's the longest one that we went down the path, and it's a blue node. We could also find all the strings with a particular prefix. For example, if I ask for all the keys with the prefix SA, what would be your answer? Sad, Sam, same, and sad. In some order, it doesn't matter what. So just as a quick exercise, how do we get all of the keys in a try? Let's take about a minute to solve this. All right. Normally, I would give a bit more time, but in the interest of time, let's bring everyone back. Did anyone come up with like some starting ideas on how to do this? Yeah.
So we can use recursive function in some sort of collection that sort of works. We have a string builder, and then as you go through whenever we input a window, we can take whatever that string is that recursive function and pop it off. Have that short collection.
Yeah, it's kind of like that. So the idea is we're going to kind of do a traversal of this entire tree. So we start off by looking at this root, and then we just start off by creating an empty list. And then for each of these keys, we call this helper function, which will be recursively called. What we do is if this is a valid key, then we add the current string that we're building into our list. And then we'll look at all the children. We'll look at all the children. And then just call the helper on them, adding the new letter to the string. So here's just a quick example. We'd call help here. Currently, the string is A. Then it goes to AW, AWL, AWLS. AWLS is a valid word according to this. So we add that to the string. And then we just kind of go back up the tree. This is kind of the same thing as a pre-order traversal. Then we look at S, SA, and so on and so forth. We get all the strings in our try. So if we want to get all the letters or all the words with a given prefix, how might we solve this? Anyone want to take a quick first idea that comes to mind? Yeah.
Use the same algorithm. We start on the node after.
Yeah. You first go to SA and then you just use the exact same algorithm, collecting all the keys from there. Yeah. So using this, we're able to get all the keys with the prefix SA. That's not something you can do with a general hash table or because you can't figure out where all the strings are. The whole point of a hash table is that they're in random locations. This one, there's a bit more structure so you can find things. Now, there's one other use case that I'd like to show. Here's just a quick demo. So I like to solve puzzles. I'm kind of a puzzle person. I do a lot of puzzles on the side. I'm actually running a puzzle hunt right now if you'd be interested. It's called Teammate Hunt, but that's beside the point. Uh, One of the things that I like to play is this New York Times spelling bee. All right. And the way that this works is that you find words that use this middle letter and which are contained only within these letters. So, for example, can someone find a word in this? Huh? Coat? Yeah. So the word coat is using only these 7 letters and it contains the middle letter. So you'll get a point for this. Any other words? IoT? That's not a word, unfortunately. It's also too short. You need at least 4 letters per word. Action. Nice. That's a good word. It's a long word. So, what if you were bored and want to cheat on this? Well, fortunately, there is a tool for use. It is called Nutramatic. And the idea is that Nutramatic lets you use random regular expressions. For those of you who took 61A, was regular expressions discussed in no, it's sometimes covered, sometimes not, depending on the semester. A regular expression is kind of just a way to decide a particular type of string. In this particular case, what I can do is I can say that I want words that contain these letters, A, C, T, I, O, N, and Z, these letters, and I want to have as many of these letters as I want. Star represents arbitrarily many of these. And if I put this in quotes, then this is going to give me all the words that contain only these letters. So we have in, a, to, on, at, it, and. If I want to get rid of the words that are too short, then I can do something like this. So this guarantees it's at least 4 letters long. So I get into, action, anti, NCAA, nation, Antonio. And I can probably also add a restriction that it has at least 1 O in it. So if I want to find a really long word, let's say that I want to find a 7-letter word at least. What do you think? Contact contains citation initiation. Ooh, ionization. Ionization. So it works. So you can kind of cheat by using this. So my question to you is, how do you think Nutramatic works? Just spitball ideas. What do you think? Which one was a pangram? Good question. In order to figure that out, I probably want to do, let's see, A, C, T, I, N, C. Okay, for those of you watching and you're playing to play the spelling bee, please look away right now. I'm about to spoil the pangram. Yeah, so that's the pangram. All right. There's also a bunch of other words that don't really exist, but you might notice that these are like ordered by size, right? In kind of the order of like how likely they are as valid words. So if you go into under the hood and see what its usage guide is, It actually explains exactly how it works. Here's also a bunch of puzzles that it also works for. But internally, Nutramatic uses a try. What it does is it takes every single word or phrase that occurs in Wikipedia, 23 million of these words, and stores it in a try according to frequency. Uh, and what it does is once it has that try, it looks down every single path that could possibly lead to something that fulfills your pattern. And it goes through a best first search, looking at the nodes that have the highest frequency first, using a priority queue of nodes to do this. This goes into a lot more detail about this. It initially contains only the root node, and as long as the queue is not empty, it just keeps taking the most frequent node, examines it, looks further, keeps going all the way down. Eventually, it manages to find the best nodes first, and then it returns those nodes until it runs out of space on the page to tell you all items. This has a whole lot of information on how this works. It even has source code that's fully not really documented that you can take a look at if you're curious. This is kind of just a way to show how the tools that we've been using or teaching you in this class can actually be used to solve some pretty interesting puzzles. So for those of you who play Spelling Bee, I have now shown you how to cheat. But yeah, this tool is actually really helpful with many puzzles in general. If you do puzzle hunts as often as I do, this is kind of your go-to resource for like figuring out what the answer is to a puzzle when you have only 5 out of 11 letters. All right. Yeah. The videos talk about Google autocomplete. They do something similar. I'm just a puzzle person, so I wanted to add a bit more of a puzzle flair to this. All right. So when your key is a string, a try does tend to be better than the normal approach. You have theoretically better performance than a hash table or search tree. You do have to decide some choices. These are kind of choices on how you build this that I didn't go over in this half lecture. The hash table is probably going to be how you like store like all of your children. If you want to go to the pre-recorded videos for more information on this. And the big important part of a try, though, is that you can solve some problems that you can't really solve with a hash set, right? Nutramatic would not work if you didn't have a try as a concept, because you couldn't like check only words that had like specific patterns. So you can use these data structures in cool ways. Nutramatic doesn't just use a try, it also uses a priority queue. So you might end up, when building something, you might end up using a ton of different data structures for different purposes. So it's important to know like all the data structures you have available and know how you can kind of mix them together to build something new. So there are other types of string sets and maps. There's suffix trees, there's DODs. We won't discuss them in this course, but there's a whole bunch of different data structures. It seems like anyone or any CS grad student who wanted to could just build a data structure, call it a thesis, and be done. So a lot of people have made a bunch of different types of trees and tries. Yeah. There's also, yeah, there's a lot of cool stuff here. All right. Any questions on tries? All right. So that concludes the try section of this. We'll now go into midterm 2 review. Same thing as midterm 1 review. This is kind of just a long sequence of slides that I've taken from past lectures. Stop me at any time with questions. Just let me know if you have anything you want to cover in more detail. This is going to be kind of a brief overview of what we've discussed. So we started off by talking about asymptotics. Here is kind of our formal definition for theta bounds. So we have two functions, and if the function is theta of another, this is true if the middle function, the R of n, is upper bounded and lower bounded by the other function times a constant. So R of n is in theta of f of n if R of n is less than or equal to some constant times f of n and is greater than or equal to some other constant times f of n. For some positive constants k1 and k2, and only for sufficiently large values of n. We don't need to worry too much about small values of n. We just kind of want to make sure that as n grows really big, the function stays up to a constant factor off from some other target function. O bounds is just kind of this one side. We're looking at the upper bound only. Omega is when we're looking at the lower bound only. We talked about how we can use this to find a runtime. Uh, and kind of the way you do that is you count the number of units of work that get done. There's a lot of different ways you can count them. Sometimes we combine them into like groups that you can easily like evaluate each, and then you find some clever way to sum them up. Other times you kind of like say that this part must be O of n, therefore this part must be n squared, so you add them up to get n squared total. There's a lot of different approaches. We didn't cover a lot of them because there's really no easy way to classify every single approach. Often it's very difficult to do asymptotic analysis. The examples that we give in class are often the simplest ones that you can evaluate. And these are often modern like research topics that even the smartest people on Earth don't know how to solve yet. This isn't a math class, but here were kind of the summations that we expected you to know. The sum of 1 plus 2 plus 3 plus 4 up to n is theta n squared. The sum 1 plus 4 plus 9, all the sums of cubes, or all the sums of squares, sorry, is theta n cubed. The sums of cubes is theta n to the fourth, so on and so forth. And then for exponential things, it's always the last term. So 1 plus 2 plus 4 plus 8 plus 16 up to 2 to the n. That evaluates the last term 2 to the n. And the same is true for arbitrary base. Now, asymptotics can be used in any math. It's not just for runtimes. It just so happens that when we're evaluating runtimes, asymptotic analysis tends to be very helpful because you can kind of ignore all of the weird things that happen when you think about runtimes, right? Depending on the computer you're running things on, you're going to get different runtimes just because my computer is 1,000 times faster than your computer. All those are constant factors. We don't care about them because we're dealing with data bounds. Any questions here? All right. We talked about a lot of types of disjoint sets. The disjoint set problem was given some graph, determine whether things are connected. And we talked about a few different variants. We talked about the quick union, where the idea is we store elements in this kind of tree structure, where each element knows its parent. To find an item set, you just go up to the root. So two items are in the same set if they share a root. And when we want to connect things, we just connect one to the other by changing one root to be the child of the other root. As it turns out, this isn't really that good because in the worst case, if you pick the wrong order of connect operations, then you get this really spindly tree that's really tall, and it takes forever to find your items. So we solved this by using a weighted quick union, where we decide that we only connect by setting the root of the smaller tree to be the child of the other. So we hang down the smaller tree. That way, we reduce the number of things that get put down at lower levels. Yeah.
That don't have any narrative like that. How do you determine like which of the two is the
Yeah. So when you're unioning like two single element trees, how do you determine which one is chosen? It's kind of arbitrary. For weighted quick union purposes, it doesn't matter which one it is. We actually showed that regardless of how you try to do things, it's impossible to get worse than log n height. So even if you make the worst possible choices to do that, you still get log n height. And that's kind of optimal. Yeah. We then discussed that we can actually do better with path compression. And what path compression does is that every time we go up to the root to find items, we find a lot of items along the way. And those items must be connected to the root, so we just connect them directly back to the root as we go up. It doesn't add much extra time. It's a constant factor difference for the find operation. But what it does is it ends up creating a tree that gets smaller as you query it often. It doesn't change the worst case runtime because you might just always pick the roots to connect every single time. But on average, you can get amortized runtime of inverse Ackermann event. where the inverse Ackermann of n is a function that grows so slowly, it's basically less than 5 for anything that's within 2 to the 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 2, repeated 2 to the 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 2, repeated 2 to the times. Yeah.
Half compression is half connect 2 and 3. Do you also connect 5 to 0 or 5 to 6?
If you path compress with connecting 2 and 3 together, nothing's going to happen here. You'll connect 2 back to the root, but that doesn't change anything. The reason why is because 3 doesn't know that it has 5 as a child, right? The only way you can know if 5 has 3 as a parent is by looking for 5 itself, and that'll take way too much time. So yeah, if you're connecting 5 and 2, it does depend on the structure or the type of weighted quickening with path compression you do. But I think the version we teach is you do all the finding and looking for first, and then you connect the 2 trees together. So you won't connect 5 and 0 quite yet. The next time, if you do is connected 5 and 2, then the 5 will see 5, 3, 0. So I'll connect the 5 directly to 0 next. Yeah. The worst case is still log n because sometimes you just pick the roots every single time. But it's only for that one occasion. Yeah. If you look at a large sequence of operations, the worst case amortized runtime is inverse Ackermann of n.
If you had a child, let's say 10, and then you connect 10 and 5, so within 10, we connect it to 0 first.
Yeah, if you had a child 10 here, and you connected it to 5, then 10 would connect to 0. We'd find 0 and 3 as the roots, and then we'd connect 3 and 0. Yeah. We also discussed binary search trees. These are rooted binary trees with the binary search tree property, which states that everything to the left is less than, everything to the right is greater than the keys. This only really makes sense if we have comparables that fulfill these properties. Namely, things must always be comparable. You can't have 2 things that are equal to each other. And you have this transitivity where A less than B and B less than C implies A less than C. This also does mean that we only will have no duplicate keys. So we won't have the same key twice in our binary search trees. So this kind of restricts us to using this only for sets and maps. We saw that depending on like how bushy the tree is, we can get really good or really bad heights. Log n height is what we would get for randomized or average cases, but for worst cases, we can get this really spindly tree that takes theta n height, where n is the number of items, and it ends up being really, really bad for our runtimes. So to prevent that, we had a few solutions. We had the B tree approach, the 2-3 and 2-3-4 tree approach, where we kind of just put multiple items into the same node, just so that we can ensure that everything is the same height. Each child or each node, if it has, let's say, 4 items in it, they'll have 5 children, 1 for each gap between items. And the idea is if a node gets too full, then we just pop one of the items up, send it to its parent, and now we have another valid B tree. And the tree really only grows in height when the root gets too big. We can show that this ends up having logarithmic height guaranteed. It's unfortunately not very nice to code in practice. So we decided to switch to this LLRB approach, left-leaning red-black trees, which is effectively a B tree, but it actually is a binary search tree. Instead of having multiple items per node, we have these red links that pretend like they glue together items. As it turns out, you can use this one-to-one mapping between B trees and LLRBs to get a tree that balances itself using rotations and color flip operations with at most log n operations per step. So overall, you can get log n runtimes for your left-leaning red-black tree, and it's actually fairly nice to code up. Any questions here? Yeah. You always insert to a leaf in a B tree? Yes, you always insert to a leaf in a B tree. Kind of the reason why is if you try to insert to one of these like middle nodes, For example, if you tried to add a new item to E, now you need to add an extra like node below here, right? Because if you have two items in a node, you need three children. You can't get a third children without doing something else. So only the bottom leaves get the added first. But then from there, you might burst and add items back up to the tree. Yeah. We talked about hash tables. Hash tables solve the set and map problem in a different way. The idea is that you ask each item to classify itself according to their hash code, and the hash code just returns some number. And based on that number, we split it into a bin. The number of bins increases with the number of items. So you have only about one or two items per bin at most. When we look for an item, we just look for the bin corresponding to that hash code. And since there's only one or two items in there, it's constant time on average. Now, it only really works if the hash code is good. The items don't mutate themselves. There's a lot of caveats, but overall, you end up getting constant time amortized in expected value. So this is kind of the gold standard for sets and maps if you don't really know much about your data, besides the fact that they have a hash code. Fortunately, Java requires that everything has their hash code. You do need to have some restrictions on how hash code works, right? You need to make sure that two things that are equal must have the same hash code. Otherwise, sets and maps break. But otherwise, things work out nicely. We had min heaps, which solve the priority queue problem. The idea is you have a set of items, you can insert new items, and you want to be able to take the smallest item at any given time. So the idea is we sort the items into this binary tree structure, a complete binary tree. And we also add this caveat that any item is less than or equal to any of their children. So here's an example of a complete binary tree that fulfills that. It's a heap. And when we insert an item, we just add a new item to this to the new location that it should go into, and then just swap items up, swimming up the item until it can no longer move up. When we're moving, we delete the top item, which is the smallest item by definition, move this bottom item up to the top, and then sync it down until it can no longer sync. So using this, we're able to solve this problem in log n time. Now, the way that we store this internally is we kind of use an array structure. As it turns out, because we have this particular structure for a tree, we don't have any way to change that structure. We can just store it as an array. The array is just faster to use than a tree because we have all the data in consecutive memory addresses. Once you take 61C, you'll learn that that takes about 10 to 100 times less time to use than nodes just randomly placed in main memory. So this is actually kind of a significant amount of runtime difference. Not asymptotically so. So we don't need to worry about that in this class quite yet. Still, overall, you get log n time amortized for all operations. It isn't log n directly, because sometimes you got to resize the array. It's not going to be a log n time operation in that case. It's going to be a theta n runtime because you need to do a multiplicative resizing. Yeah. We talked about some traversals. When you have a tree, you can traverse the tree in various different ways. The idea is you are trying to look at every single item. So for trees, especially binary trees, there's three main ways that we do things: pre-order, in order, and post-order. It's kind of like you look at your left child, you look at your right child, and you choose whether or not you look at yourself before you look at anything, in between when you look at anything, or after you look at anything. So depending on that, you can get different orderings, and each one has its own unique advantages. Depending on the problem you're trying to solve, you're going to want to use different ones. We also showed that there was this kind of trick where if you kind of draw around the tree, then depending on whether you're on the left, when you hit the left side, the bottom side, or the right side of the item, that's kind of the order in which you'll see the pre-order, in-order, or post-order traversal. It's kind of a trick. It's not really generalizable, but it's useful like shorthand if you're like really strapped for time. And it only really works for binary trees. Finally, we've kind of talked about graphs. And graphs were these things with a set of vertices, edges, adjacencies. Each vertex or edge might have a label that tells some value associated with it. We had paths associated with it, and simple paths don't have repeated edges. cycles were things that just go back to their original self. Uh, and then we talked about connectivity. There's a lot of different problems that you can solve with the graph. These aren't really designed to solve a specific problem. They're more used to like take a problem, translate it into a graph world. And once you're there, you tend to have an algorithm that can solve the problem for you. So there were a number of these problems that we found, right? The disjoint sets problem, right? Determining if two things are connected. We were able to solve that in inverse Ackermann time if we got rid of some of the structure of the graph. There were some other problems that we solved. And depending on the problem, some of them might be easy, some of them might be hard. It's often really hard to tell the difference between the two. For example, the shortest path problem, we were able to solve that. What's the name of the algorithm we used to solve that? Dijkstra's. The longest paths problem, finding the longest path, that one turned out to be impossible. In fact, if you solve it, then you earn $1 million. So there are a lot of different ways you can traverse things, similar to with trees. We had DFS depth first search, which is kind of like you look at yourself, then you recursively call this DFS on each child in succession. So you look at items down the path as you go, looking at your one child before you look at any other child. The post order is the same thing, except you look at the recursive calls to each child first, and then you look at yourself. We actually discussed on Monday how DFS post order was useful for finding a topological sort, but that's not in scope for the midterm quite yet. And then we had breadth first search, where we kind of use a queue to look at items steadily farther from the start. So we look at items 0 distance away, then 1 distance away, then 2 distance away, and so on, growing our fringe outwards over and over. Here was Dijkstra's algorithm, where we find the shortest paths tree, where we add items into priority queue, and then we just kind of relax these according to which ones are closest to the source. A star was similar, except instead we have a target goal and some heuristic that tells us approximately how far it is to travel that distance. And instead of looking at items in order from how far they are from the start, we look at how far they are from the start, plus how much time it's expected to get to the goal. So the minimum lower bound on how much time it takes to get to our goal. And we discussed how sometimes, depending on your heuristic, you might have an A star that works perfectly, or doesn't work at all, or is just the same as Dijkstra's. In particular, if A star just has a heuristic that returns 0 every time, then you're back to Dijkstra's. It's exactly the same as Dijkstra's. But generally speaking, for like map purposes, we can get a good heuristic for this. We also talked about yeah. Are you expected to be able to find a heuristic? No. We will tell you what your heuristic should be, or we'll give you a way to compute it, right? So we might give you like a grid and say that the heuristic is the straight line distance, right? Yeah. So we also talked about the minimum spanning tree problem, which is to find a spanning tree that hits all of the nodes, and every edge, or the total sum of the edges is as small as possible. We talked about both prims and kruskalls as ways to solve this problem. Here is kind of our list of all of our graph problems. And here's the other graph problems that we solved. These are just kind of quick tables that if you want, you can add to your cheat sheet, hint, hint. These might be useful just as a way to have some of these things memorized. And then we also had a bunch of these data structures that all have different uses. Most of these are on your reference card, so you don't need to write them on your cheat sheet, but they are still useful to think about in terms of what they're useful. All right. Any last minute questions? All right. In that case, good luck on the midterm.